Welcome back to Fundamentals of Visualization. In our last video, we took a peek at what are some of the basic practices behind choosing how we map our data values to visual elements in a visualization. However, we also saw that there are a number of visual channels and different decisions that one might make when they're actually constructing the visualization and constructing these mappings between our data and our visual channels. So while mastering the ability to effectively map data values to visual elements is a lifelong process, today I want to share just a few basic tips for effective choices for mapping data in your visualizations. So I want to start today's lecture by just recapping a little bit, what do I mean when I talk about a mapping? And as a reminder and refresher from our last video, mappings are functions that translate values from one space to another. In the case of visualization mappings, we're translating from our data space to our design space. And we're doing so by choosing our encodings and choosing the mathematical functions we use to go between data value and visual channel. So sometimes when we're making this choice, we end up in situations where, because of the distribution of our data, we end up with a skewed mapping. A whole lot of our data maps to one particular range of the encoding. For example, here in this graph, I have this kind of exponential pattern, which means that most of the variation down here below 6 on my x-axis just generally gets lost. So one trick that I have in my toolbox for choosing an effective mapping between this kind of skewed or abnormally distributed data would be to do something like choosing to map my data to a log scale. So mapping our graph to a log scale, we get something like this, a straight line. Well, this is really simple to think about and conceptualize in a position space like I see with this line graph. Log scales can actually help us resolve details in other kinds of mappings as well. For example, if I have this heat map here where I've mapped my data to color on a linear scale, I can see that I get some variation on the right side of this heat map, but the left side looks all to be pretty much the same color. However, there's actually a lot of rich, interesting variation going on this map as well and in this data, and we can recover some of that interesting variation by, again, mapping this data to our log scale. One of the tricks when we're trying to use log scale mappings is that log scales are really handy for resolving details in our skewed data distributions, but they can make it a lot harder to read. People, generally speaking, don't think in logarithmic terms. So this is one careful thing to think about when you're choosing to use log scale mappings. Another set of tips I want to go over really quickly is this idea of how do we actually choose the way that our data values map to our visual channels. Some of the visual channels that we might use, like size, shape, or color, actually have special constraints we need to consider when we map data to them. So I'm going to walk through just a few of these constraints to give you a basic intuition about some effective practices for mapping between your data values and these kinds of visual channels. The first one we're going to look at is one of probably the most commonly violated constraints when we're thinking about visualization mapping, and that's this idea of mapping to size. When we map to size, we can often map to length. For example, in a bar chart, we might map to the length of the bar, and that's a pretty intuitive way of showing our data. Most people have a pretty good sense for what's going on when they see a bar chart. However, you'll also see visualizations like bubble charts that map data to the area of a mark. So to illustrate what this looks like, let's talk about a quick example. So I have two groups of people, Group A and Group B. Group A has about 10,000 people, and Group B has 20,000 people. So what we know from just looking at these numbers is that Group B is about twice as large as Group A. So if I choose to represent the size of Group A and Group B using the size of my marks, if I encode those values using the diameter of the mark, so the height of the bubble in this case, what I actually end up with is something like what I see here, where in reality, B is 4 times as large as A. So when I choose to represent my data using this diameter, I'm actually getting 4 times the number of blue pixels for B, even though the values are only twice as large. However, if I encode my value using the area, I get what I see over here with the purple marks, where B is actually twice as large as A. So there are 2 times the number of purple marks, or purple pixels, as there are in B as there are in A. So what this ends up meaning is that my perception of the relative differences between A and B is much more accurate if I encode values with size using area versus if I were to use the diameter or the height of a bubble. Another channel that has some interesting considerations when I'm starting to think about mapping values to visual elements is shape. So shape has all sorts of interesting facets and features. We can think about how many edges are present, how many sides, what kinds of angles are used. Do I have a right triangle versus an isosceles triangle? I can also use shape for qualitative data. That's probably the most common place you will see shape being used. I have a group of values that maybe represent birds that are mapped to circles, that represent dogs are mapped to squares, and that represent cats are mapped to triangles. However, you can use shape to try to represent more continuous data, so our more numeric data. One technique for doing this is something called a cuton that you see here. So these are 2 diverging scales that use both shape and color to try to represent data. In this case, if data is increasing, it's shown in white. If it's decreasing, it's shown in black. And you can see that the complexity of the shape, whether it be adding more line segments in the case of this top set, or whether it be adding more edges or more complexity to the shape itself in the case of this bottom set, it increases as I move further to the extremes. So in this case, when you map these kinds of representations to a large field, let's say I'm overlaying this on a map, my texture density gets much, much denser, and my ability to sense this intuitive quantity of more actually increases with the systematic increase in the complexity of shape. So this is one way that we can use shape to try to encode quantitative, numeric, continuous data. Motion is another channel that is possible to map to a whole variety of different visual parameters. I will caveat all of this by saying I recommend using motion sparingly. It's very, very hard to attend to lots and lots of moving things. In general, we're not very good at attending to lots of moving things that are moving disparately in different directions, and we're not very sensitive to changes in motion, in large part because when something moves, I have to remember where it was. And human memory is fairly fallible, as we'll see in our later discussions of perception. But if you're in motion, if that's something that's engaging, it's visually compelling, it's something you want to experiment with in your own visualizations, we can map motion using a number of different factors, including velocity, acceleration, and direction. So if I'm looking at velocity, I'm basically trying to understand how quickly do 2 points move. If they move at the same speed, that generally means that they have the same value. If I'm looking at acceleration, then my 2 points end up in the same position, but one of them tends to move faster at some point in the motion than another. So that's how I would be looking for the differences, is looking for the rate of change of speed. And finally, probably the most common way we'll see motion encoding value is through direction. So I can have 2 dots that are moving in opposite directions, which implies opposite values. Like I said, motion is something I recommend using sparingly, but if you're interested in using motion, these are some of the ways that you can break down the idea of motion into effective encoding channels for data mapping. We can also map using texture. Texture tends to be an encoding that emerges from the sheer construction of our visualization itself. So when we're looking at texture, much like motion, we have a number of different attributes of our texture that we can choose to map to data. In particular, 3 of the most common are density, variation, and pattern. So when we look at texture density, that's essentially how much of our texture, or how tightly packed is our texture for a particular data value. So for example, here I can see that the blue square on the left has a much tighter texture density than the blue square on the right. So that tends to be correlated with higher values. We also have the variation. So here we can see for these green squares, the green square on the left has stripes that are going up and down. The green square on the right has stripes that are going right and left. This kind of texture mapping tends to be very useful for qualitative data, where we just want to be able to distinguish between different categories. But if we want to take this idea of texture mapping to the extreme in qualitative data, we'll often do something like what we see with the purple cubes here, where the purple square on the left has just a straight up different pattern. We have these different diamonds inside versus different squares inside. And these differences in pattern can indicate different categories of value. Texture is, again, one of those channels I recommend reserving for less important variables just because we're not very well attuned to it. But one thing to pay attention to is that textures will often emerge in your visualization. So thinking about how you can design and choose marks and create visualizations that allow for these interesting patterns and textures to emerge as a function of your data is one thing that you can do to try to ensure effective overview, to ensure that people get the big picture of what's going on in your data at a high level very quickly and very easily. So the final channel that I want to mention briefly that has special constraints is color. For color, we're often talking about one of three dimensions. We're talking about hue. So this is essentially what name is the color. Is it red? Is it orange? Is it green? You have chroma, which is how saturate is the color. Is it very gray and dull, or is it very bright and saturate? And then we have luminance, how light or dark is the color. We can manipulate hue, chroma, and luminance in really interesting ways that result in different kinds of communication about the patterns that are in our data and about the data values themselves. And this idea of how do we work with color and how do we work with these different attributes of color is going to be the topic of our next video. So I look forward to talking with you more then.